And we will now have the first presentation from a member of the Z-Level team, and that is Arun Das. He's a product owner at BMW, and he will present the simulation use cases that we already heard about by Stefan. And let me give you some facts about Arun. So he's indeed responsible for the simulation use case 1, and he's responsible for the tool development coordination platform OpenPath, and also an advocate for the open source collaboration. Arun, welcome.
Thank you, Laura. I have the honor to present the simulation use cases in Z-Level to you today. I feel honored to do that as it is a central element in our project. And as we have heard, simulation use cases have popped up quite some times already in the first 2 presentations. And that points out how important they were to us. Actually, the simulation use cases originated from the fact that in the project, in the very beginning, we had a lot of different work packages. They were all individual, they all had their own focus, but we didn't have anything in the beginning that kept everything together. And that is when we came up with the idea to implement simulation use cases based on real-world applications, real tasks that could originate in the different houses of our partners. And that's when we said, okay, let us implement this simulation that incorporates all the different work results from the Z-Level project. And to make sure that we cover a wide range of applications, we said we'll do 3 simulation use cases, as we have already seen by you, Stefan. Throughout the project, we realized simulation use cases are not only good for us internally, but actually these are also great showcases or demonstrators to present to you today what all we have achieved and how this could be used in practice. And that's where I want to start. Actually, in the beginning, let me show where within our fields of action we need to locate the simulation use cases. And you can see there's quite a lot of red color in this image. In our case, this is a good thing, just because the simulation use cases have the goal to touch anything and everything that we did in Z-Level. And I'm pretty sure we achieved that. And throughout my presentation today, I'm trying to point out to you where we incorporated the different elements of our project and how this became a few big simulations in the very end now. So the presentation is structured in a way that, first of all, we'll have, again, an overview and some motivation for the simulation use cases. And then I want to dive a little deeper into the 3 use cases we implemented and the different demonstrators that have originated from that. Afterwards, we will also take a closer look at which models have been used, how they have been used by the use cases and the simulations we built up, and also what important role architectures and standards play in that. And we've heard how important it is to collaborate, to have these open standards and build up on them. And I'm pretty sure that with our simulation demonstrators here, we are able to give you a visual idea of how this works in the end. And yeah, in the end, we will also have a summary and an outlook. And I'll especially refer to the virtual exhibition booths that are happening afterwards. So stay tuned for that. We have seen this V model once before. With our simulation use cases, as I have said in the beginning, we aim at having practical realizations of different simulation tasks. In our case, we decided to cover especially the area of analysis tasks and test cases, which can be strongly supported by simulation. And we apply Z-Level results where, for example, implementations and tools play a huge role, similar to the models that have been developed in the project. Aside from that, also methodologies and processes are incorporated. This focuses, for example, on the credible simulation process, which has been applied to the simulation use cases as well, in order to make sure that whatever we do there is also traceable for later reconstruction, for example. And last but not least, we applied best practices from the Z-Level project. We relied on an architecture that was aligned throughout the project. We relied on the standards that have been developed and extended. And we used that for ourselves throughout the project to test if what we develop works in practice. That was our internal goal. But at the same time, we realized, let's take these simulations and show them to you and show them to the public in order to visually show how this can work in practice. And in this Veeam model, we can locate the 3 simulation use cases quite well. The first one is in the top left corner. It's the simulation use case 1 that focuses on system analysis. Now, in our case, we decided to do a criticality analysis, which mainly focuses on finding critical scenarios in a larger scenario space. Once I have identified critical scenarios, I know these are important scenarios that I need to consider during development, but also when it comes to testing. So this could be a great input for simulation use case 2, where it comes to the test of an automated driving function. In our case, this was done in a closed-loop simulation, focusing on the test of this integrated system composed from multiple individual components. And as a third simulation use case, we decided to go more into the details. So we kept the simulation quite small. It's a component test, a single component that is the system under test, but it is simulated in great detail. And we will see what that means based on the examples for camera, radar, and LiDAR sensors. And we did not only implement those 3 simulation use cases once, but we implemented them several times under small variation in different tools to make sure that this is not usable only in one tool, but it can be exchanged, it is modular, and based on those standards and the architecture understanding that we have developed, it can actually be applied in different tools, which is our main goal long term, to not be restricted to a certain tool or a certain process that we want to apply. And therefore, we have demonstrators from IPG, from DSpace, we have an implementation by the DLR with their research implementation of a tool chain. We have OpenPath in the project, and also ETAS has contributed with a Kala implementation. But we will see later on where this has been applied. This picture, we have already seen it before. I want to point out where to locate the simulation use cases in this matrix that shows the huge space that we operate in. We have a wide range of engineering tasks, and we have an operational environment that, Stefan, you just answered it also in your last question, which is really big, which is basically infinite. And therefore, we tried to locate the simulation use cases in this matrix to indicate what areas we cover with them. And you can already see that it covers quite a lot of that matrix. Simulation use case 1, the closed-loop traffic simulation for an analysis task, is located within the column of analysis engineering tasks. But it starts from a subsystem which plays a huge role in the simulation. It also incorporates an overall vehicle system because we tried to run an automated driving function in that scenario. We come to traffic nodes, and we even extend that to traffic networks, as you will see later on, because we used a quite complicated map in that example that could already be considered a traffic network. Simulation use case 2 with the closed-loop test of an automated driving function can be located between testing and releasing. And this has the clear focus on a system under test, which is this driving function, which incorporates subsystems into an overall vehicle system. And of course, we need some surrounding environment as well, where there is a small and rather simple junction in that case, which we consider the traffic node for this example. And then simulation use case 3 with the detailed sensor simulation is focusing strongly on the component, which is tested in some traffic node, in some simple crossing as well. And now, as we have located the simulation use cases, let's really take a close look at them. We'll start with the first simulation use case. Afterwards, we will cover simulation use case 2 and 3 to give you the overview of all 3 of them. And as I've said, really detailed information on the simulation use cases will later on be also available in the virtual exhibition booths. The criticality analysis that has been executed in simulation use case 1 is shown in the images. We see that there is a big and complex crossing. This crossing consists of pedestrian crossways, a lot of different lanes coming into the crossing and leading out of the crossing, and traffic is controlled through traffic lights. Within that environment, which is defined by an OpenDrive description of the map, we embed our vehicles and our pedestrians. In this case, we decided to have a highly automated driving function incorporated. So we have one vehicle which is equipped with this function, and this vehicle is told to turn left. During the left turn, the vehicle has to consider oncoming traffic as well as other pedestrians which are moving in this simulation. So you can already see there is a lot of different elements that come into play when executing the simulation, and this shows how complex it is, not only for setting it up, but also for the individual models like the automated driving function, the agents that act around the automated driving functions, the surrounding vehicles, the surrounding pedestrians, to make them behave in a realistic way in the simulation. And we decided to model this based on agent behavior models. That means that the vehicles are controlled by so-called driver models, and the pedestrians are also called by human behavior models, which imitate human behavior. This, for example, allows to also observe non-normative behavior as some special case in the simulation, and it especially allows for interaction throughout the simulation. What we did is, with our goal, or to achieve our goal of a criticality analysis, so to find critical scenarios, we had to apply variation in the simulation. So what we did is we varied the initial positions and the initial velocities of the different vehicles, and then we ran the simulation over and over again, several thousand times actually. And every time we ran it, we again changed some parameters, some velocities were changed, some initial positions were changed, and that's all we had to do, because the rest of the interaction was modeled by traffic behavior models, and they react to each other. Therefore, we see realistic traffic just like it happens in reality, and we were able to find certain critical scenarios based on the setup. In the bottom right corner, we can, for example, see an evaluation. We were evaluating time to collision and post-encroachment time here to measure the criticality, but more on this will be shown in the virtual exhibition later on. To summarize it, in the simulation use case 1, we applied stochastic parameter variation based on this complex scenario, set up based on agent behavior models. Everything was executed with the OpenPath tool, which is an open source tooling. And we were able to run this simulation several thousand times and found various critical scenarios. To give you an impression of this, I have a small video, and I hope that it works to play it. Yes, there we see it. From the top left corner, we can see the ego vehicle arriving. This is the automated driving function. It's the white car that now starts turning. And we could already see that it had to brake to let the oncoming traffic pass before it turns. Now there's even another car turning right in front of it. And small dots are moving, which are our pedestrian models. So we can see that there are even pedestrian models crossing the street. And based on our variation, we saw cases where the pedestrians were far away and didn't even interact too much with our other vehicles, and there were simulations where it was really close. Small teaser for later on, there will be more videos in the virtual exhibition booth available where you can see how the variation impacted this simulation. Now let's move on to simulation use case 2. Simulation use case 2 was the closed loop traffic simulation, was the closed loop test of a highly automated driving function. The main goal here was not to set up a fairly complex simulation, but the main goal was to set up a test case that you could have in reality as well. And therefore, the decision was made to let the automated vehicle turn right at this crossing that is shown in the bottom left corner. To have some sort of interaction, we placed a pedestrian and a truck in the scenario as well, which are moving and require the ego vehicle, the system under test, to react to those other traffic participants. Within this simulation, the main interest was to show how to take different models, for example, a highly automated driving function, couple it with some motion controller, and in the end have some vehicle dynamics for simulating the overall toolchain in the virtual world. And this integration had, of course, to happen based on standards, which was the challenge in this case. For this simulation, object-based sensors have been used, but actually several object-based sensors. Therefore, even sensor fusion had to be applied in this simulation case. The simulation use case 2 also introduced fault handling, which is a rather complicated task, especially when it comes to using standardized interfaces where somehow these fault triggers need to be incorporated. More on this can be seen in the virtual exhibition booth regarding simulation use case 2. And actually, there's 3 demonstrators that came out of this simulation use case. The first one is the research implementation provided by the DLR. We also have DSpace with their Simfera toolchain and IPG with their CarMaker tool. The 3 demonstrators that originated here do not execute the exact same simulation, but they also did minor modifications on each one of them. And therefore, you'll be able to see some different simulations from that side. Also for this simulation, I brought a video to give you a first indication. In this case, the video is from the DLR research implementation. We can see how the automated vehicle is coming from the left side and had to wait, especially for this pedestrian that was crossing there. Additionally, we had some other surrounding traffic here to make it a realistic test case. Now that we have seen 2 closed-loop simulations, I want to also point out an open-loop simulation, the simulation use case 3. This simulation use case was focusing on the component simulation of sensors, meaning camera, radar, and LiDAR. And the simulation was built up based on physically based sensors. That means real sensor effects as they occur in reality were also brought into the virtual world. And sensor realistic simulation has been executed, incorporating ray tracing, incorporating reflections, and it was investigated by looking at sensor detections, by applying object tracking to those simulations. And therefore, the different tools that have been used, like DSpace Aurelion, ETAS with their COSIM, and open source implementation Carla, but also IPG with CarMaker, were executing these simulations with different sensor technologies. And they managed to integrate the sensor models that model the physical effects in great detail, even within an FMU, which is following the FMI standard, therefore provides an aligned interface to the outside world, and can be incorporated also based on the OSI standard. And here I have one example that shows in the video again the depth image that was generated from a simulation of a camera sensor. I can already tell you there's also videos available on object tracking. And also for radar and LiDAR simulation, there's videos available that show how the ray tracing works and how reflections have been modeled. So that's more things that you can investigate when talking to the people at the virtual exhibition booths later on. Now, what does that mean for the models that we have developed in Z-Level? We have developed quite a lot of different models, and they have been used throughout different simulation use cases and also other activities within the project. The models that have been developed, they're listed here on the slide, are not just used once, so to say one model is developed for one application, but the model was developed in a rather generic way in order to use it in different applications. And this is something we were again able to demonstrate as we have multiple simulations implemented. And also we see that different simulations have different requirements. That's, for example, the reason why radar, camera, and LiDAR sensors are not only modeled as, why not each one of them is modeled once, but why we have two models for a radar and two models for a LiDAR, because one of them is object-based for when the sensor effects do not play a huge role in the simulation, and we have the physically based sensors, where it really comes down to the physical properties of the sensor and the technologies that are underlying here. Now, one more time, I want to compare here the three simulation use cases. We have seen one is an analysis case, we have two test cases, we have closed loop simulation, we have open loop simulation, we have also seen different tools have been applied. Of course, always targeting what is the overall goal that the simulation has to achieve. Let me point out the main points for the complexity, where the complexity for the simulation use cases arises. Simulation use case 1 had the complexity in the overall setup, complex map, a lot of agents, agent behavior models that interact with each other. So the goal to enable for realistic traffic. Simulation use case 2 was mainly focusing on integrating different models in a vehicle system by incorporating a HUD function, a motion controller, a vehicle dynamics model, and coupling all of that together so that it can be used in simulation as an overall chain. And simulation use case 3, as we have just seen it, focused on the sensors and therefore was focusing on doing the physical realistic simulation with everything that comes into play here. We have also heard that the architecture is a quite central element. Here we can see at a first glimpse that the architecture, based on the generic architecture that we came up in the project, can be realized in different ways always depending on which simulation I want to conduct. And from a high-level perspective, I know we cannot read what is shown in the architecture itself, but I want to give you the impression that looking from a high-level perspective, we can see similarities. And that's exactly the goal that we want to achieve with the architecture. We want to have the common understanding where to have cuts, where to have interfaces, how to encapsulate logic in the simulation, and therefore how we can set up individual simulations from generic building blocks, so to say. And that's why when we look at the three different architecture images of the three simulation use cases, we can see a lot of similarities, how this was set up. And also we can see, for example, for the component testing, of course, this is a different picture. We have a rather small simulation, but the individual blocks are filled with more logic and more details due to the realistic simulation of sensor effects. And to set up something like this, to have this simulation set up and also to have an architecture like this, we need to speak a common language. And that common language is defined by standards. We have seen, or we have heard also about the OpenX standards by ASAM, mainly OpenDrive, OpenScenario, which are used to define the map, to describe what should happen throughout the simulation in OpenScenario. Also, OSI helps us to communicate with simulation models as it defines messages that can be sent back and forth. And then we have FMI as a shell, which can be used to embed logic in some sort of a box with a standardized interface to the outside. This is actually shown on the right with the example of a pedestrian model. Here we have the simulation model encapsulated as an FMU following the FMI standard, and everything communicates through OSI messages, which is the way of transferring data back and forth. And then we have Open Material as yet another standard that was used for the sensor simulation, which allows to define vehicle or surface properties and material properties in a standardized way in order to make it available to sensor models. And SSP is a standard that is used to compose several models, usually FMUs, in a larger network of FMUs. And with that, I would like to come to the end and summarize what we have seen about the simulation use cases. Simulation use cases were for us a tool to generate feedback within the project, to test if whatever we develop works in practice. But it turned out it's also a great showcase for you. That's why we're presenting it today and tomorrow throughout the event. We have seen what important role the standards play in this. as everything is based on standards and also based on a generic architecture which is our common understanding on how to set up a simulation. And a lot of those tools and the simulation models will afterwards also be available to the public through open source projects. Therefore, they will also be available to you if you want to set up similar simulations as we did. And with that, let me just refer to the exhibition booths that you can visit if you want to get more information. We have exhibition booths targeting on the simulation use cases and also on specific topics like scenario and maps, fault handling, and many other topics that I have covered throughout this presentation. And with that, I would like to thank you for your attention. And thank you very much. Yeah.